In the stillness of the Harvard Astrophysics Laboratory, Dr. Helene Sullivan peered at the dataset that had just arrived from the Event Horizon Telescope. The year was 2019, and humanity had just captured its first image of a black hole, specifically, the supermassive black hole at the center of galaxy M87, some 55 million light-years from Earth. But Dr. Sullivan was not looking at the famous orange ring that had captivated the world's attention. She was examining something else entirely, subtle patterns in the radiation that seemed to defy our fundamental understanding of causality. "Frank, you need to see this," she called to her colleague, Dr. Frank Jacobs, a theoretical physicist specializing in quantum gravity. Frank adjusted his glasses as he approached her workstation. "What am I looking at?" he asked, squinting at the screen. "These radiation patterns from the black hole's ergosphere, they are exhibiting temporal anomalies consistent with Wheeler-Feynman absorber theory," Helene explained, pointing to what appeared to be reversed energy signatures in the data. The theory she referenced was not new, developed by physicists John Wheeler and Richard Feynman in the 1940s. It proposed that electromagnetic radiation could, in principle, travel backward in time. Most physicists considered it an elegant but ultimately impractical mathematical model. But the data before them suggested something profound might be occurring in the extreme environment near M87's event horizon. Our conventional understanding of time has undergone radical transformations over the past century. Prior to Einstein's 1905 publication of special relativity, most scientists viewed time as absolute, ticking forward at the same rate for everyone, everywhere in the universe. Einstein shattered this notion by demonstrating that time is relative, flowing at different rates depending on relative motion and gravitational influence. By 1915, his general theory of relativity revealed that gravity itself is not a force but a curvature in the fabric of spacetime caused by massive objects. The more massive the object, the more it warps the spacetime around it. Black holes represent the extreme example, regions where gravity is so intense that spacetime curves back upon itself, creating a boundary called an event horizon beyond which nothing, not even light, can escape. The math suggests time could actually run backward in certain relativistic reference frames, Frank mused, but we have never observed direct evidence of it. What Frank and Helene were contemplating touches on one of the most perplexing aspects of modern physics, the arrow of time. In almost all the equations that govern the fundamental forces of nature, electromagnetism, the strong and weak nuclear forces, and gravity, time is symmetric. The equations work perfectly well whether time runs forward or backward. Yet our lived experience tells us time flows in only one direction. We remember the past, not the future. Coffee cools down, it does not spontaneously heat up. Broken eggs do not reassemble themselves. This one-way direction of time is often explained by the second law of thermodynamics, formulated by Ludwig Boltzmann in the 1870s, which states that entropy, a measure of disorder in a closed system, always increases over time. This appears to give time its arrow, pointing from the past, lower entropy, to the future, higher entropy. Yet near the event horizon of a black hole, the conventional rules begin to break down. As Dr. Kip Thorne, Nobel Prize-winning physicist who worked on the theoretical underpinnings of gravitational waves, has demonstrated in his research, spacetime becomes so severely warped that our intuitive understanding of cause and effect can be challenged. "We need to run simulations based on these observations," Helene said, already typing commands into her computer. The team spent weeks analyzing the data and building models of what might be happening near the supermassive black hole. Their findings suggested something remarkable. In regions of extreme spacetime curvature, particularly near the ergosphere, the region just outside a rotating black hole's event horizon, there exist frames of reference where thermodynamic processes might appear to run backward. This is not merely a trick of perspective. In 1969, mathematician Roger Penrose proposed a process called the Penrose process, by which energy can be extracted from a rotating black hole. This occurs because in the ergosphere, spacetime itself is dragged along with the black hole's rotation, creating what physicists call frame dragging. In this region, an object would need to move faster than light to remain stationary relative to distant stars, an impossibility according to special relativity. "The implications are staggering," Frank said one evening as they reviewed their simulation results. "If entropy can locally decrease in these regions without violating the overall increase of entropy in the universe, then we might need to reconsider our understanding of temporal directionality." What Frank meant was that while the universe as a whole continues to increase in entropy, there might exist local regions where, from certain reference frames, entropy appears to decrease, where time, in effect, runs backward. To understand this counterintuitive concept, consider a thought experiment proposed by physicist Richard Feynman in the 1940s. Imagine watching a film of two particles colliding and then bouncing apart. If the film were played backward, the physics would still look perfectly valid. Particles approach each other and bounce away. At the quantum level, most particle interactions look the same whether time runs forward or backward. But when we scale up to macroscopic objects, this time symmetry seems to disappear because of entropy. A shattered glass does not spontaneously reassemble itself because there are vastly more disordered arrangements of glass shards than ordered arrangements forming an intact glass. However, in the extreme conditions near a black hole, particularly one as massive as M87's, 6.5 billion times the mass of our Sun, as measured by the Event Horizon Telescope collaboration, spacetime becomes so warped that the ordinary progression of cause and effect might be locally reversed. The research team brought in Dr. Eleanor Martinez, an expert in quantum thermodynamics from MIT, to consult on their findings. What you are describing, Dr. Martinez explained after reviewing their data, reminds me of recent experiments with quantum systems where we have observed negative entropy production. She was referring to groundbreaking work published in 2019 by researchers at the Brazilian Center for Research in Physics, who demonstrated that in certain quantum systems, entropy can temporarily decrease without violating the second law of thermodynamics. This occurs because quantum systems can become correlated in ways that classical systems cannot, allowing for what appears to be a local reversal of the thermodynamic arrow of time. If similar quantum effects could be amplified by the extreme gravity near a supermassive black hole, she continued, it might explain your observations. The team's findings connected to another puzzling phenomenon in quantum mechanics, retrocausality, the idea that events in the future might influence events in the past. Experiments like the delayed choice quantum eraser, first proposed by John Wheeler in 1978 and implemented in laboratories by 2000, suggest that measurements made in the present can affect how we interpret the past behavior of particles. Helene realized they were treading in territory few scientists had explored empirically. We need to design an observational test that could confirm or refute our hypothesis, she said. The team developed a proposal to observe high-energy particles near the event horizons of multiple black holes, looking for statistical patterns that would indicate temporal reversals in particle behavior. Their methodology relied on analyzing polarized light from jets of particles ejected by black holes, searching for signatures that could only be explained by localized time reversal. In 2021, the LIGO-Virgo collaboration, which had first detected gravitational waves in 2015, earning the Nobel Prize in Physics for Rainer Weiss, Kip Thorne, and Barry Barish in 2017, announced the detection of gravitational waves from a black hole merger with unusual properties. The signal contained harmonics that suggested the merged black holes had created regions where spacetime was not just curved but twisted in ways that affected the temporal ordering of events. Helene and Frank's research suddenly gained new relevance. Using data from both LIGO-Virgo and the Event Horizon Telescope, they identified patterns consistent with their hypothesis. In the extreme environments near certain black holes, particularly rapidly rotating ones, there existed reference frames where thermodynamic processes appeared to run in reverse. What we are seeing is not time itself flowing backward throughout the universe, Frank explained to a captivated audience at a physics conference in 2022, but rather localized regions where the arrow of time points in the opposite direction to what we experience on Earth. This research connected to work by theoretical physicist Sean Carroll at the California Institute of Technology, who has extensively explored how the arrow of time relates to the initial conditions of our universe. Carroll has proposed that the low-entropy state of the early universe, which appears to have been extraordinarily ordered compared to the present day, establishes the cosmological arrow of time we experience. But if black holes create regions where local entropy gradients can be reversed, it raises profound questions about the nature of time itself. Is the forward direction of time merely a consequence of our universe's particular initial conditions? Could other regions of the multiverse, if it exists, experience time differently? The implications extend beyond astrophysics. Quantum gravity, the as yet undeveloped theory that would unite quantum mechanics and general relativity, might need to accommodate the possibility of bidirectional time. This connects to loop quantum gravity, a theory developed by physicists Carlo Rovelli, Lee Smolin, and Abhay Ashtekar starting in the 1980s, which suggests that spacetime itself is not continuous but composed of discrete atoms of space. In Rovelli's book The Order of Time, 2018, he argues that at the most fundamental level, time as we understand it might not exist at all. What we perceive as time flowing might be an emergent property arising from complex quantum interactions, rather than a fundamental aspect of reality. By 2023, Helene and Frank's research had gained significant attention. NASA approved a mission to gather more data on the ergospheres of black holes using specialized satellites designed to detect subtle quantum fluctuations in high-energy radiation. If we can confirm that time reversal occurs in these extreme environments, Helene explained in an interview, it would not just be an exotic curiosity. It could help us resolve some of the deepest paradoxes in physics, including the black hole information paradox. The black hole information paradox, first formulated by Stephen Hawking in the 1970s, arises because black holes appear to destroy information when they evaporate via Hawking radiation, a process that seems to violate quantum mechanics, which requires information conservation. If time can flow backward near black holes, it might provide a mechanism by which information could be preserved. The research also connected to recent advances in quantum computing. In 2019, researchers at Google claimed to have achieved quantum supremacy, performing a calculation that would be practically impossible for conventional computers. Quantum computers exploit quantum effects like superposition and entanglement to process information in ways classical computers cannot. If time reversal is possible in certain reference frames, it suggests new approaches to quantum computing that might exploit temporal effects rather than just spatial quantum properties. Theoretical quantum physicist Nicole Junger-Halpern of Harvard University has pioneered work in quantum thermodynamics, which examines how quantum systems exchange energy and information, potentially allowing for the temporary reversal of entropy in controlled environments. The universe is not only stranger than we imagine, Frank quoted physicist J.B.S. Haldane during a presentation of their findings, it is stranger than we can imagine. Yet despite the mind-bending implications, the research remained grounded in empirical observation and mathematical rigor. Each hypothesis was tested against observational data, and the team was careful to distinguish between established science and speculative interpretation. In 2024, a new generation of gravitational wave detectors came online, including the space-based LISA, Laser Interferometer Space Antenna, mission, providing unprecedented sensitivity to the subtle ripples in spacetime created by cosmic events. These detectors confirmed patterns in black hole mergers consistent with localized time reversal in ergospheres. The picture that emerged was revolutionary yet built on the solid foundations laid by Einstein, Wheeler, Feynman, Hawking, and others. In the most extreme environments of our universe, near the event horizons of black holes, particularly spinning ones, spacetime becomes so warped that the arrow of time can point in the opposite direction to our everyday experience. This does not mean that causality is violated on a cosmic scale. The universe as a whole still increases in entropy. But locally, in these extreme environments, observers in certain reference frames would perceive events occurring in reverse order, effects preceding causes, entropy decreasing rather than increasing. The implications extend beyond physics into philosophy. If time can flow backward in certain reference frames, what does this mean for concepts like free will and determinism? If the future can, in some sense, influence the past, does this suggest a kind of cosmic predestination? As Helene put it in a 2025 interview, we are not saying you could travel back in time and change history. What we are saying is that the distinction between past, present, and future is more fluid than we previously thought. In certain extreme environments, what we call the past and the future might be observer-dependent in ways we did not anticipate. This research also provides new perspectives on the cosmos at large. Our universe began in the extremely low entropy state of the Big Bang and has been increasing in entropy ever since. But if black holes create regions where the entropy gradient is reversed, they might represent something like cosmic reset buttons, localized regions where conditions approach those of the early universe. Some theorists have even suggested that black holes might give birth to new universes, with each black hole in our universe potentially spawning a new cosmos on the other side of its singularity. If time flows backward near black holes in our universe, perhaps it flows forward in these daughter universes, creating a cosmic cycle of time arrows pointing in opposite directions across different universes. The discovery that time might flow backward in deep space does not overturn everything we know about physics. Rather, it enriches our understanding, revealing the universe to be even more subtle and complex than we had imagined. The laws of physics still hold, but their manifestations in extreme environments challenge our intuitions about the nature of reality. As we peer deeper into the cosmos, using ever more sophisticated instruments and mathematical models, we continue to discover that the universe is not just stranger than we supposed, but stranger than we supposed possible. The flow of time, once thought immutable, joins the growing list of phenomena that, upon closer inspection, reveal surprising flexibility. In the depths of space, where gravity reaches its most extreme, time itself becomes plastic, stretching, bending, and even reversing in ways that remind us how much we still have to learn about the fundamental nature of reality. The arrow of time, it seems, does not always fly straight.